Admittedly, I almost didn't do this problem because it's kind of a pain, to be honest with you, but then I thought, you know, if it's kind of a pain to me, then it's probably going to be a pain to most people. So I want to go through the problems that are also a little bit painful to show you that they're not painful if you do them and think about them logically. So here's the problem. It doesn't look too bad, but then when you start getting into it, there's a bunch of little places where you can go wrong. So here's what we have. A balanced three-phase load. It says 3 balanced three-phase loads are in parallel. So first, right off the bat, your head is spinning, because we don't have just a single three-phase load. We have 3 three-phase loads. So think about, you know, a Y load, a delta load, and then some other load. 3 different three-phase loads, and they're all connected in parallel. So that's kind of crazy just to think about it. It tells us that load 1 is a Y load. And here's the impedance per load, 400 plus J, 300 ohms per phase. That's load 1. But in parallel with load 1 is load number 2. It's a delta load. So not only are the loads in parallel, they're different loads. We have a Y load up here connected to a delta load in parallel underneath it. And you might think, well, how can you connect them? Aren't they different? Well, think about it. 3 lines go in and connect to your Y load. 3 lines go in and connect to your delta load. So literally you can go and have 3 lines connected to a Y load and then tap off of those guys, drag them down in parallel and connect your delta load. And then take those 3 lines in parallel with those, drag them down and connect to a third load. So it's like one load connected to another load in parallel, connected to another load in parallel. But each of those loads is 3 phases. So it's 9 elements kind of connected, sort of, if you want to think of it that way. So load 1 is Y load, load 2 is delta load. Load 3 doesn't even tell us if it's Y or delta. It just says it absorbs 172.8 plus J 2203.2 kVA. So in other words, it doesn't tell us if it's Y or delta, it just tells us how much power that third load absorbs. And then it gives us some other information. It tells us the line impedance is 2 plus J 16 ohms. Okay, cool, I know what the line impedance is. And then it tells us the magnitude of the line to neutral voltage is 24 times the square root of 3 kilovolts. That's a weird number, but it's just a number. And it's the magnitude, it's only the magnitude. It doesn't tell us what the phasor quantity of it is or anything. It's just the magnitude of the line to neutral voltage. So that's weird. Okay, it's just a weirdly constructed problem with 3-phase loads in parallel. But what we're asked to find, we're just going to focus on A and then we'll come back to B in a minute. We're going to find the total complex power at the sending end of the line. What that means is, you got to visualize it here because I don't have enough board space to actually draw three-phase loads in their entirety in parallel with one another. I don't have enough space, so you have to use your imagination a little bit. But you have some generator here. You have 3 lines, A, B, and C, that come over here, and it's connected here to a Y load, just like every other Y load we've ever done, okay? But then underneath that, we tap off from those 3 lines and we connect to a delta load, and underneath that, we tap off and we connect to some third load. So the first is a Y, the second's a delta, the third one's a black box. We don't know what it is, but we know how much power it absorbs. And then we have some other information, but we're asked to find the total complex power at the sending end of the line. So we have, in other words, generators, and the sending end of the line is right to the left of the line. So we want to find out, essentially what it's asking you is how much total complex power is absorbed by the line plus all of those loads. That's what it's asking you. And you have 3 of them in parallel, so it's even more complicated to think about. So the way to do it is, what you need to do is you need to you got to draw a single phase equivalent circuit. There's no way that you're going to be able to draw this thing. You can draw it, but it's just going to be really weird to draw it. All 3 phases, all 3 loads connected in parallel. So I'm going to show you how to draw a single phase equivalent circuit with multiple loads in parallel. We haven't done that before, but it's straightforward when we actually do it in a second and think about it. So just kind of get it in the back of your mind that we're going to draw a single phase equivalent circuit, and we're going to use that to calculate the power absorbed by every element, the line, load 1, load 2, and load 3. And once we have all the powers in place for everything for the A phase, we're going to multiply by 3, and that's going to give us the total complex power at the sending end of the line, because that's going to be for all 3 phases. All right, so let's kind of roll up our sleeves and get to work. So we have to draw a single phase equivalent. We know what the line impedance is. Okay, cool, that's easy. This is going to go in the top part. I'm not going to draw it here. I'm going to draw it on the other board. Load 1 is just going to be this impedance. It's already a Y load. We know that Y loads can go straight into the single phase equivalent, so we're just going to draw the first load exactly as it sits. But the second load's delta, and we definitely cannot use this number, this impedance, in our single phase equivalent because it's a delta load. We have to transform that. So let's take a moment down here to write down for load 2, we're going to have to do a delta to Y transformation, which means that the equivalent Y load is going to be this guy divided by 3. So it's going to be 2400 minus J 1800 divided by 3. So the equivalent Y load is going to be 800 minus J 600. Okay, done. So again, reviewing things so far, we're going to have a line, and we're going to have a single phase equivalent with this guy for the first load, and then for the second load, we're going to use this transformed Y version of it in our single phase equivalent. What the heck are we going to do for this third load? Well, you don't know if you have no idea if it's delta or Y. But we remember from the last problem, I emphasized over and over again, whether it's a delta load that's really inside that black box, or if it's a Y load that's really in that box, it almost doesn't really matter because this is a power problem. What we really care about is what is the power absorbed by that third load, right? Whether it's delta or Y doesn't really matter because what the problem's asking us is, what is the total complex power at the sending end of the line? So we're going to add up how much power is absorbed in the line, how much power is absorbed by load 1, how much power is absorbed by load 2, and how much power is absorbed by load 3. But we don't know if it's delta or Y, but that's okay because we don't care because all we're going to do is add it to the other things that are absorbing power, and it tells us right here it's absorbing this. Now here is part 1 of a great place to screw up this problem. Because if you, it's going to be hard to describe until I draw the picture in a second, but basically this load 3, it says it absorbs this many kVA. It doesn't tell you it absorbs this much per phase. So what you have to do is read between the lines a little bit. For this guy, this is the impedance per phase, this is the impedance per phase, this is the power, but it doesn't say per phase. So what you really need to make sure and do is say this is the total power among all 3 phases of that third load. But what we really want to do in our single phase equivalent when we write it down to keep it all straight is we really want to write down 1/3 of that. Because a single phase equivalent is written down for only one phase. The A phase, which will include load 1, load 2, and load 3's A phase. So when we write down how much power is absorbed per phase, because, yeah, in the end we're going to multiply by 3, but I'm just saying to keep it straight in the single phase equivalent, we want to write down 1/3 of this because this is the total power absorbed by all 3 phases, but the single phase equivalent is only written for one phase. So I guess what I want to do is down here for load 3, what I want to do is I just want to take that guy, the 172.8 plus J 2203.2. I want to divide that by 3 also. Not because we're transforming it like we did here, but because this is the total power over all 3 phases. But in our single phase equivalent, I want the power per phase. You'll see why in a second. It's going to be 57.6 plus J 734. Whoops. If I can write 4 down correctly, 734.4. Don't forget the units, it's kVA, kilovolts. I'll take care of the kilo part of it in a little while, but for right now, let's just divide by 3. So now, believe it or not, we have enough information to write down a rudimentary, basic single-phase equivalent. It's going to be kind of tough to get it all down, but you got to remember there's a source over here, and so connected to that source is going to be an A terminal, and then you're going to have an inductive guy right here. This is the line, and the line was given to us in the problem statement, 2 plus J16. So this is 2 ohms, and this is J16 ohms, okay? Then you have load 1. Load 1 is going to be something like this. Load 1 is a Y-connected load, so it can go straight into our single-phase equivalent, 400 plus J300. This is ohms per phase. So it'll be 400. Like that, 400, J300, just like that. Then we look at load 2. It was a delta load, so we could not put this directly in our problem, but we transformed it by dividing by 3, so this is what we want to put. We want to put 800 minus J600. So we drag that off. Where do we write it? There's lots of different ways you can do it. You could hang it off in parallel, like I said, but I'm going to make it a little easier to read by doing it like this. So it's going to be something like this. This is load 2. So what we're going to have is 800 plus J600. 800 J600. Okay, you kind of have to get used to it. If the problem only had two loads in parallel, then we would stop here. We would say this is a single phase equivalent circuit. And we would say that IAA is the line current. This goes through here. The only problem or difference is that when the line current gets here, it splits and it goes through these loads because they're in parallel, and it recombines and it goes back through the source. You got to get used to the idea of whenever you have a problem that tells you that you have multiple loads in parallel, your single phase equivalent circuit looks like this. It's like you cover this thing up completely and you just write down the single phase equivalent for the first load, and then you have another load in parallel, so you add it to it, right? That's what the single phase equivalent would look. But in order to add it to it in parallel like that, they have to be Y loads, just like they do for any single phase equivalent. But now we have a third load. This is the total power it absorbs, but since that's a single phase equivalent circuit, we divided it by 3. This is the number we want to put. How the heck do you represent that? This is how I do it. You may do it a different way, that's fine. What I do is I come off in parallel, because we know it has to be in parallel, and I come over here and I draw a box. I don't know what's inside the box. I really don't. It could be a delta, it could be a Y, whatever. It could be hamsters running around in a circle. But what I know is that it is 57.6 plus J 734.4, and that's kilovolt amps. Make sure and carry the kilo because you're going to ultimately have to blast that out times 1,000 because you want to have everything in VAs, volt amps, ohms, and base units to do the calculations. So this is actually the single phase equivalent circuit, believe it or not. You have a line impedance, you know the line current's going to go that direction. You know you have a generator over here. You have load 1, you have load 2, and you have load 3. So just to kind of keep it straight, because we're going to label it like that, we're going to say this is load 1, this is load 2, and this is load 3. Now, what else can we glean from the problem statement? It says the magnitude of the line to neutral voltage. Now, don't forget, this is the other part. You got to look at these. Yeah, we spread it all out, but all of these things on the bottom, they're all tied together at one point. We draw circuits where everything's spread out and kind of coming back and connecting, but this is literally connected to this. This is literally connected to this at one point. That's what we call the neutral terminal there. So really, capital N is the common point over there on the other side. So capital N, I'm going to write it, I guess I'll write it here. And lowercase n will be over here somewhere where the generator is. Uppercase n is where all of them come together, right, for the A phase, and so on, up there. The reason I write it there is because it tells us the magnitude of the line to neutral voltage is basically going to be from here down to here. The line is up here to the neutral, which is where everything ties together down here. The magnitude of that was given in the problem statement as 24 square root of 3 kilovolts. I don't like writing in kilovolts, so I'm going to write it down as 24,000 times the square root of 3 kilovolts, but I have to choose something in this circuit as a reference. You know, it only gave me the magnitude, it only told me what the magnitude is, but I don't know what the generator is. I have no idea what that is. I don't know any other voltages in the problem statement, so I'm going to just use this as a 0-degree source. All it means is everything is relative to it. Now, I know I'm writing it next to the inductor. What I'm trying to say is that the voltage between the line to the neutral is equal to this magnitude. I'm going to go and stick a phase there because I'm going to use it in a calculation, and the calculator is going to assume a 0-degree phase anyway if you just put a number in there. So I'm going to go ahead and choose it as my reference at 0 degrees. That's how you interpret it. A lot of people say magnitude of line to neutral voltage is equal to this, and you don't know where to put it on the drawing because this is a really weird looking single phase equivalent. So I'm teaching you load 1, 2, and 3 are in parallel. Where they come together at the bottom, that is still the neutral terminal. So when you say line to neutral, that is the voltage across, look, across all of them. Voltage across this is this, which is the same as the voltage across this, which is the same as the voltage across whatever is in this box that's absorbing that much power. So now that you have that written down, the rest of the problem is actually straightforward. All of the problem complexity for this guy is boiling down to knowing how to write it down, and knowing where to put that voltage, knowing this is the neutral terminal, and so on. Because what we're asked to do is find the total complex power at the sending end of the line. In other words, we want to find what is the complex power absorbed here, plus whatever's absorbed here, plus whatever is absorbed here, plus we already know what's absorbed here, so we'll just add that. We add all of those together, and that's going to be the complex power by one phase, because this is a single phase equivalent. So we get that number, multiply by 3. That gives us the total power absorbed by everything to the right of the generator. So we have to work per phase, and that's why now you understand why I wanted you to divide it by 3 to put this in the box, because if I would have put the other number in the box, I would have confused me. I would have accidentally added it and then multiplied it would have been too big. So I divided by 3 to get it here, to put it on equal footing with everything else we're going to calculate on a per phase basis. Okay, so how do we find the power absorbed by load 1? Well, I guess I need to talk a little bit more about the roadmap here. There's actually a lot of different ways you can do this problem. There's a lot of different ways you can do this problem. What I'm going to do is I know the voltage across this, so I'm going to use it to calculate the current through this leg. And then I'm going to use, because the same voltage is connected in parallel here, so I can calculate the current through this leg, right? And then I'm going to also use this voltage with this power information to calculate the current through this leg, even though I don't know what's in the box. So I'm going to calculate all of these currents. Why? Because I need to know the current through the line also. And I need to know that current to calculate the power here. So yes, I know you could do V squared over Z here and V squared over Z here to find the power directly. I know you know the voltage and you know the impedance. That's true. You could find those powers right away. But I'm not going to do that because I have to find the currents anyway, because I'm going to add them all up with Kirchhoff's current law to find the current flowing through here, which I have to find the current through the line. Okay? So what we're going to do is we're going to find the current flowing through load 1. So I'm going to write that down as I, load number 1. V over Z, just like Ohm's law, right? It's going to be 2400 angle, whoops, forgot the square root of 3, because that's part of the number, angle 0. So V over Z, and this guy is going to be 400 plus J 300. Okay? So what you're going to get when you do that calculation, I load 1 is going to be equal to 83.14 angle negative 36.87 amps. So that literally is the current for the A phase going down here in this single phase equivalent circuit. Now, how do I find the current flowing through the B phase? Or not the B phase, sorry. The current through the second load over here, load 2. Load 2. Same thing. I is equal to V over R, V over Z, whatever you want to say. So this is going to be 2400 square root of 3, angle 0, divided by this impedance, 800 plus J 600. When you do that calculation, you get, let me just double check my math here, make sure I didn't write anything wrong. Oops, it's a minus 600. And I found a very small mistake here. It's actually not big enough for me to want to go back and edit things or change things. I'm just going to show you, I'm human also. In my original problem statement, load 2 was this impedance, minus J 1800. I divided that by 3 and I got 800 minus J 600. But in my actual load, what I put here was not minus J 600, I put positive 600. So that's actually wrong. I caught it when I looked back at my paper. So really this is not J 600, this is negative J 600. So that means when I calculate this current, there's a negative sign right there. So I just want to make sure you understand that that's why I changed things right in the middle there. So when I take the 24 root 3 angle 0, divide by that, I'm going to get 41.57 angle 36.87 degrees. So that's the current going through here given by this, the current going through here given by this. How the heck do we find the current going through here? Well, when you think about it, you know that for load 3, it's a power relation of some kind, right? So you know that any power can be written as VI conjugate. Now I know the power absorbed by this black box, so I know what's on the left-hand side. I know the voltage across that black box, so I can find out what I is. So all you got to do is plug things in. So on the here you have on for the power it's 57.6, but that's kVA, so you have to multiply by 1,000. So it's going to be 57,600 plus J. Then you have again 734.4, so you multiply by 1,000. 734,400. I know big numbers are not fun, but that's just the way it is. And then over here, that's equal to the voltage across it, which is already in volts, so that's a good base unit, 24,000 root 3 angle 0. And then it's times I conjugate. So here's how you solve an equation involving a conjugate. You have the left-hand side, which is a complex number. You have the right-hand side, which is a phasor. And then you divide them like that. What you get on the right-hand side is I conjugate. And I conjugate is going to be, when you do that division, 17.72, angle 85.51. So that is not I. That's not the current I. That's I conjugate. So to find the actual I, it's 17.72. At an angle, you flip the angle. Negative 85.51 degrees. Okay. So now we have I of load 3. So now we have I of load 1, I of load 2, and I of load 3. What was the purpose of all of that stuff? Now that we know we have a line current coming in, it obviously splits off into 3 branches and comes back. So we can do a Kirchhoff current law right here at this top node. Everything's connected together at the top to find out what this IAA is, the line current there is. So basically this current is going to be the sum of this one plus this one plus this one. So we're just going to add them up. That's just Kirchhoff current law. So we're going to write that down as KCL. The line current AA is equal to the current going through load 1 plus the current going through load 2 plus the current going through load 3, which we've already found all of those. So IAA equals 83.14 angle negative 36.87. I'm literally just writing them down. 41.57 angle 36.87 plus, and then the last one's 17.72 angle negative 85.51. Literally, that is just load 1 plus load 2 plus load 3. You just add them up because of the way the drawing is. The current's coming in, so it's got to be equal to the sum of the load currents there. So then you find out what this line current is. I told you this problem was going to be a little bit of a pain, sorry. But that's just the way it is. 109.76 angle negative 22.84 amps. Okay, so that is the line current through here. So now we can actually make some progress. Now that we know the current going through this impedance, and the current going through this impedance, and the current going through this impedance, and we know the power here, we can calculate power here, power here, power here. We already have power there. We add them all up. And that's going to be the power per phase for everything on the right-hand side. All right, so what we're going to have is, the complex power per phase of all of this stuff is going to be equal to the power dissipated in the line plus the power dissipated through load 1 plus the power dissipated through load 2 plus the power dissipated through load 3. That's how I'm going to write it down. So the power per phase is equal to, what would it be for the line? We now know what this current is. It's I squared Z, magnitude I squared Z, right? Magnitude I squared is, this is going to be, the magnitude of this is 109.76, so 109.76 squared times that impedance 2 plus J16. This is the magnitude of the current flowing through the line impedance, squared, of course, right? And then what you're going to have is, for this guy, you're going to have the current going through here, magnitude is 83.14, flowing through here squared times this impedance. So you're going to have 83.14 squared times that impedance, 400 plus J 300. Then you have the current flowing through this impedance, which is the magnitude of it is this, 41.57, square that times this one. And you'll add it to the sum, which is going to be 41.57 squared times that impedance, 800, minus J 600. And then, so now we have this power, this power, this power, and this one we just write it down because it's already, we know the current going through there, but we already have the power, so we just write it down exactly. So we say that last power is going to be 57,600. Now we multiply by our 1,000 to get everything in the same equal units of power. J734,400. Volt amps, and then this will be volt amps, volt amps, volt amps. All the units should be consistent. So I'll switch colors, and then we'll have the total power absorbed by the load for one phase is going to be the sum of all that stuff. Multiply, 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 add everything together. What you're going to get is a big number. It's going to be 4,229,050 plus J 1,963,995. Yes, I'm aware of significant figures and all that stuff, but really I just want to keep it, I want to keep all the decimals. You guys can truncate it however you want, but I'm just going to do that for right now. VA. Okay, so this is the power per phase. Question didn't say power per phase. It said, what is the total complex power at the sending end? So the total power is going to be, total power is 3 times that number that we just wrote down. So what it's going to be is, let's write down, 3 times this giant number, which is going to be 12,687,150 plus J 5,891,985 volt amps. And then I'll round a little bit here just to match what most of you were, go back to kilovolts. Because here, the original problems were in kilovolts. We got giant numbers here. Let's go back to kilovolts. So we're going to move our decimal point a little bit. It'll be 12,687.1. I just kind of truncated it right there. 687 decimal 1 plus J 5,892.0 kVA. Basically, I had to cut it somewhere, so you guys will cut it different. I rounded that, made it a 2, and then the decimal point there, and then here I basically made this a 7.1. You know, you guys can round differently however you want, but that's what I did. And I changed it so that it would be kVA. So this is going to be my answer that I'm going to call my answer. So 12,687.1 plus J 5,892.0. Again, the rounding can be a little bit different. This is the total power absorbed by everything to the right of the source, the line plus all 3 loads. And it required a lot of little bitty steps to get there. You know, a lot of places where you could make mistakes. First, we have to know that in order to make a single phase equivalent, we have to use Y loads. So this one's good as is, but we have to divide this one by 3. Then we also have to divide this one by 3 to put it in our black box, because this is the total power across all 3 phases of this third load. So then we draw our single phase equivalent circuit, right? And then we have to recognize that this voltage, this line to neutral voltage, is the same voltage across all 3 parallel parts of this guy. Then we find load current 1, load current 2 for Ohm's law. Load current 3 we find by using the power relation VI conjugate. We set it all equal, we find I current 3. Then we add all 3 of those currents up to find the current through the line. Add all 3 currents up to find the current through the line. And then once we have all the currents everywhere, we say the total power per phase is I squared Z for the line, I squared Z for load 1, I squared Z for load 2, plus the load 3 power that we already written down. Add all of them up to get that big number, multiply by 3 for all 3 phases, get a giant number, and then we basically divide by 1,000 and round to get the total power absorbed across all 3 phases. That's part A. Part B is actually much, much, much shorter, so it's not a very big deal for part B. Part A was by far the hardest part. Part B, what percent of the average power at the sending end of the line is delivered to the load? What percent? What they're basically saying is you have a generator and you have some line losses. So these loads are the important things that we really want to send the power to. Load 1 could be a house, number 1. This could be house number 2, and this could be house number 3. Obviously, we want all of the power to go to all the houses. We don't want to lose power in the lines. That's a waste, you know? But we have calculated the total power absorbed by everything, including the line. So what we want to find out is what fraction of all of that power is actually making it here. And that alternatively is going to tell us how much we're losing in the line. So we've already done the hard part. We've calculated the total power absorbed everywhere, including the line. Now we have to take a fraction of what's actually absorbed in these loads. The only real gotcha that you have to realize, though, is that it's asking what percent of the average power. In other words, the first part of the problem asks us the complex power, but the second part of the problem is asking what is the percent of the average power, not the complex power, just the real power P, right? Now, fortunately, in our calculation, on a per phase basis, this is the real power absorbed per phase of everything. But the rest of our calculations, we're dealing with complex power. So what we need to do now is we're going to do a ratio that's going to involve this number per phase. We want to find the real power absorbed in each one of those. So what I'm going to do to find that quickly is, because I've calculated the complex power, but I wrapped it up into this calculation. It's kind of hard to see the answers. What we're going to do to calculate the real power absorbed here is going to be I squared, which we have, times this, just the resistance right here. That's going to give us the real part. Then I squared of this current times this resistance, and then we'll find the, we already know the real power absorbed here, 57.6. So we'll find real power, real power, real power, and then we'll do a ratio with the total real power of everything that we calculated before. A little bit cumbersome, I know, but you know, it is what it is. So the power absorbed by load 1 is I squared Z. Magnitude of I squared Z, but really for the Z, I'm just going to put in the resistor, just because I only want the real power. So really it's going to be I squared R. So the magnitude, or I should say load 1 current 83.14, that's a magnitude. So 83.14 squared times, again, if I put the whole impedance in, I would get the complex power. I could do that, sure, no problem. I'm just going to put the real power, because that's all I care about in this problem, 400. And I'm going to get P1, a big number, 276490384. It's a big number. Then the power of load 2 is going to be I squared Z again, but the current going through load 2, the magnitude is 4157. 4157 squared. And because I only care about the real power, I'm going to multiply by 800. That's going to give me the real power part, I squared R. And what I'm going to get for P2 is an even bigger number. It's going to be, oh no, it's not a bigger number because the current's smaller. It's going to be 1382451.92. I know I'm keeping a lot of decimals because I don't want to run into truncation errors there. So that's the power with load 2. And then the real power absorbed by load 3 is just given what's in the box, 57.6 times 1,000. So it's 57,600. That's watts, this is watts, this is watts. So these are the powers, the real power absorbed by load 1, load 2, and load 3, right? And then we've already calculated the real power, this per phase, that's just for one phase, because we're just going to do a ratio here. So we're going to look on a per phase basis, how much power, real power is absorbed by the load versus the total real power, including the line. That number per phase is this, including the line. 4229050. That's including the line losses. So how much power makes it to the load as a percentage is going to be equal to the sum of all of these things. So it's going to be 2764903.84 plus this one, 1382451.92. I'll just do it like this, plus 57600. We're adding up all the power that makes it to the load, and we're dividing by the total power, the real power of the lines plus the loads, which is, we've already done that here. So basically it would be the sum of those three plus the line losses, which I could do I squared Z here also. I could do I squared times 2 just to get the real part, but we've already done it here because we did the complex power for everything and we came up with this for the real part. So I'm just going to use that answer, and it's going to be 4229050. And when you multiply that times 100, you get a percentage, and the percentage you're going to get is 99.43%, which is what you expect. You expect most of the power to make it to the load, otherwise you've done a very bad job at engineering your system. You should have low resistance in the lines or impedance in the lines and so on. So the trick to this problem, as I already said for part A, was getting the single phase equivalent down. For part B was realizing that they wanted the percentage of the average power, which means P, only P, at the sending end versus everything else. We had already calculated the total power of all of this stuff, the complex power, so we already have the real part of that with this number per phase, right? So since we're doing a ratio, we just want to find out how much makes it to the load per phase. if you do it times 3 and do the ratio when you've multiplied both things times 3, you get exactly the same percentage. So on a per phase basis, this is the total real power. And then on a per phase basis, this numerator is the power that makes it to the load. So this is slightly bigger, slightly more power because you're dissipating some in the line also, but it's pretty darn close to this. When you do that division and multiply, you get 99, you get 0.9943, which is 99.43%. So we have done a tremendous amount of work. I mean, honestly, three-phase circuits is not an easy concept. I tried my best to make it understandable and also a little bit fun as you can make this stuff. Can't really say it's super fun. But I've tried to mostly make it understandable. And the only way that I can wrap my brain around these things is to write all the equations down, to really understand where they come from, and to solve a lot of problems. And you inch forward with your confidence when you do it that way, because then you understand, okay, I did that right, so I know what that's for, and then I do the next thing right, and I know what that's for. So unfortunately, you might be a little nauseous after watching so many lessons of three-phase power because we've worked so many problems. But if you follow me through, you should have a pretty darn good feel for how to go about doing it. If I had to give you a single piece of advice for these kinds of problems, it would be, if you can draw a single phase equivalent, do it, if you have enough information, because that will give you some credit and it will very often tell you the direction that you need to go. Remember your voltage and current shifting formulas. If the phase current and the line current are different, you can convert between the two on the load side and on the source side. If the phase voltage and line voltages are different, like in the Y case, Y loads, then convert with that square root of 3 rule. And then for the power calculations, yes, of course, we had some of those specialized equations that we used occasionally, but most of the time, you're just going to be doing VI conjugate, VI conjugate, VI conjugate, or alternative variations, I squared Z, and things like that for most things. You just have to keep track of what currents are where. If you're operating on a per phase basis or not, multiply by 3 to get the total. When they say things like total, they mean all 3 phases. And then when you have crazy things like loads in parallel, you have to still draw your single phase equivalents. If you did not draw this diagram, I think it'd be really hard to get this problem correct, to be honest with you. If you don't draw it and see, oh, there's this, I know what the power is, I know what the voltage across it, I can find what this current, oh, I can add the currents together, I can get that. That thought process of getting from A to B to C to D is not something that most people, including me, can just figure out by looking at a problem. When I look at a problem, I don't know what to do right away. But I know I can write that single phase equivalent, and I know I can find that line current, and then I know I can shift that line current, and then I know I can do da-da-da-da-da-da-da, and then I get there. I don't get there from the outset. So practice these problems. Do every one of these problems we've done in this class together, or by yourself, I should say. Check your work. And if you don't get it, then just keep working it again until you do and solve additional problems. I hope you've enjoyed this batch of lessons. Follow me on to the next set of topics. I think I'll be covering transformers here in a little bit, and that's a whole other ball of wax by itself. But for now, I hope you've enjoyed three-phase circuits, practice your problems, and good luck in your studies. Learn anything at mathandscience.com.